All right, so I'm going to take you through again like we've done, looking for patterns. And the patterns are going to be, we're going to use really easy functions, and you're actually going to say, why in the world would you do that for that function? Because you should just do it this way. It's a lot easier. I know that. I'm picking easy functions so that we can see the pattern, and then we can use the pattern for really hard functions. Okay, so the first part of the lesson is just recognizing patterns. I'm actually not proving anything to you today. We're just looking. So I could start off with, and again, if you want to write down all the examples from the pattern, that's fine, but you don't have to. The important thing is that you're following along looking for the pattern, not so busy writing that you're not noticing the pattern. So you could do this function, I'm sure, and you might say that we would like maybe FOIL it out, right? Like distribute it all out. What would you get? So 30x plus 25. Okay. And you could easily take the derivative, right? Right? Okay, thanks. Now, there's Johnny Shortcut, and he's always making mistakes. All right? Do you guys have this stuff in like the SAT books, like Joe Bloggs and Careful Kate, and like, yeah, so Johnny Shortcut. So Johnny Shortcut would say, hey, you know what? I'm going to use the power rule. I'm going to say that this is, I'm going to say that this is 2 times 3x plus 5 raised to the first. Can you see why Johnny Shortcut might think that would work? Yeah. He's wrong, though. He's mistaken. Okay? He's wrong. As a matter of fact, if you do this, he only gets 6x plus 10. Yeah, go ahead. So if Johnny Shortcut just multiplied his answer by 3, he would actually have had the right answer. Shh! Nothing yet. So Johnny Shortcut is mistaken, and we could adjust Johnny Shortcut's method. So let's look. 1 does not make for a pattern. We need to look for a few more. All right, so if we did 5x plus 1 quantity squared, you would say, oh, let's factor that out. And that would be 50x plus 10, right? Now, over here, Johnny Shortcut doing the same problem might say, hey, that's 2 times 5x plus 1. Do you understand, like, he's using the power rule? Yeah. I don't know if I made that clear. Like, he's doing the power rule. Well, Johnny Shortcut gets 10x plus 2, and that's not quite 50x plus 10, but if he multiplied by 5. Shh. All right. So, all right. So there are some of you calling out, which makes me think, do some people see the pattern? Maybe. All right. So we should do a few more. Again, 2 does not make for a pattern. X squared plus 3. And let's see. If Johnny Shortcut were to do this problem, he'd say, oh, it's going to be 2 times x squared plus 3. We know better than Johnny Shortcut. Now, this is a good question. Can you figure out what's going to go here before we do the other side? I hear 2. I hear 1. I hear 2x.
2x. Yeah. Because the...
Shh.
That's a good one.
All right, so there's not a consensus, but a majority maybe that it's 2x. Let's see. If I were to factor this out, it would be what? X to the 4th plus 6x squared?
Yeah.
All right, so the derivative is... All right, so is it true if I put a 2x here, what would I get? I would get 2 times, that would be 4x, so I'd get 4x cubed plus 2 times 3 times 2, 12x. So the 2x was right.
Isn't that funny?
All right, so now it's about time. We're going to do a few more, but now it's definitely time to start seeing the pattern. Like, it wasn't just 1 or 2, but now that we've done 3, you starting to see it a little bit? Well, okay, so here's the thing. If it's cubed, why is that not a good one to get you to see the pattern?
Because that's hard to do. It's hard to like factor out.
It's hard to factor out. So if it's cubed, right, so if it's cubed, the rule that we think we see for the shortcut will work, but I can't show you that it's true. I mean, I could show you it's true. It would just take a lot of distributing. Gabby?
If inside the parentheses, if it's like x cubed plus 3, would it just
be I don't know. Let's take a look at... All right, we could do that, actually. Okay, so... Hold on. So Johnny Shortcut might say, oh, that's 2 times x cubed plus 2x. Hey, how you doing?
Sorry,
Sure.
times 3x.
Maybe this one was too hard to do.
Actually, it has to be...
It would probably be 3x squared, maybe?
All right, so let's see. Let's see. All right, so if we do this out, we would get what? X to the 6th plus...
I'm not going to go with that. I have to write it down.
4x to the 4th?
Yeah.
Plus 4x squared? Is that true?
Yeah.
No, I'm good. So I would get 6x to the 5th plus 16x cubed plus 8x.
Oh, that's right.
That would be 6x squared times x cubed plus 2x. I gotta tell you, there's no way I'm gonna multiply those together and get 3 terms. Alright.
Yeah, because that's the...
So, wait, first of all, do you see how 3x squared's wrong?
Yeah,
Like it's not gonna work? Alright. If this would just start erasing, which it won't. Oh my goodness. Okay. So, Derek's saying 3x squared
Plus 2.
plus 2.
Yeah.
Alright, so let me, I'm going to multiply this. I'm going to get 2x cubed plus 4x. And then I'm going to get 3x squared plus 2. And now I'm going to, so I get, firsts, I get 6x to the 5th. Outers,
You're going to get
4x cubed. And inners, I'm going to get
12x
12x cubed. So that's going to be 16x cubed. And then the lasts,
8x.
plus 8x. So Derek was right. So 3x squared plus 2. Ah!
It's not like giving away something.
No, it is giving away something. We just all say the rule.
Alright. What's every single time when Johnny Shortcuts wants to take the shortcut, what does he actually need to make it right?
He's just finding the derivative of the previous equation.
Okay. Alright. So, do you see that that's where the 3, the 5, the 2x, the 3x squared plus 2 came from? And as a matter of fact, if you think about it, I'm going to write it a little differently, but when we did this, didn't we do e raised to the 3x? And wasn't the derivative e raised to the 3x times 3? Isn't that a little bit of like a Johnny shortcut?
Yeah.
Right? So what is the derivative of 3x? 3. Okay. So I'm ready to put it in a rule, and you're not going to like it, I think, in symbols. And we'll talk through it, and we'll do some examples. But this is what the rule is in symbols, and it's called the chain rule. And it really is more of a strategy than a rule. As a matter of fact, the chain rule is something that you always have to think of now. You always have to ask yourself, do I need the chain rule? So the chain rule says this. The derivative of a composite function, f of g of x, right, is the derivative of the outer function with respect to the inner function, and then chain on the derivative of g of x. And a lot of students don't like that in terms of just notation. Can we do an example to show what this means? All right, so remember from pre-calc, like if I told you g of x equals like x squared plus 3 and f of x is equal to x to the 100th, if I said, what is f of g of x, you would say?
X to the 100 squared plus 6. Oh, I was doing it backwards.
I think you were.
X squared plus 3 to 100.
Is that okay? Do people see that that's what f of g of x is?
Yeah.
So the chain rule says if I want to take the derivative of f of g of x, if I want to find the derivative of that, I need to take the derivative of f of x. Well, f of x is the raised to 100th power rule. What's the raised to 100th power rule? That's 100 times whatever it is to the 99th power. So that's this piece. That's the derivative of f of x with respect to g of x, where g of x is the inner function. And then chain on the derivative of g of x. Well, what's the derivative of x squared plus 3? 2x.
When you say the derivative of f in respect to g of x, you're not multiplying that?
No, because we're not really taking the derivative of f of x, right? Because the derivative of x would just be 100x to the 99th. We're taking the derivative of f when you plug g in. So when you plug g in, we're taking the derivative as 100 times whatever g is to the 99th. Sometimes we refer to these functions as inner and outer functions. G of x is the inner function. Do you see how x squared plus 3 is sort of inside?
Mm-hmm.
It's what you do to x first. If I said, here's a rule, what do you do to x first? Square it and add 3. That's the first thing you do. Then what do you do to it? After you square it and add 3, what do you do? No. Say it again, Adrian. Raise it to the 100th. That's the outer rule. That's what you do later. So the first thing is the inner function, x squared plus 3. That's g of x. The second thing is the outer function, f of x, which is to the 100th power. All right, so we have an outer and an inner. Now, 7 out of 10 times, the inner function will be in parentheses. Sometimes it won't, though. So, like, just as a reminder of the problem we just did, when we said e to the 3x, it's not definitely screaming to you that there's an inner and outer function. But if you think to yourself, okay, what am I doing to x? What's the first thing I do to x in this problem? Multiply it by 3. Do people see if I give you an input of x, the first thing you have to do is multiply it by 3?
Yeah.
All right, so that's the inner function. So I'd put like a little parentheses around it. Then after we multiply by x by 3, what do we do? Other way around. Raise e to it, right? So the outer function is e to the. Well, what's the derivative of e to something? E to the something. What's the derivative of the inner function? 3, right? I mean, we've done this like 8 times now. But
So you could get, like, it doesn't have to be like f of, it doesn't have to be in the form, it doesn't have to say f of g of x.
It's probably never will.
Yeah.
Okay? And that's the hard part, is you mentally thinking what's the inner and what's the outer function. All right? So that's the challenge. And that's what makes this rule more of a strategy. And it makes it a little harder than the ones we've done before. If it helps, I'm not saying you have to, if it helps, you can start thinking about it like, okay, well, g of x is 3x and f of x is e to the x. So f of g of x is e to the 3x. Like if that helps you. I always think about it as inner and outer. What's the inner function? What am I doing to it first? What's the outer function? All right. I want to do like 18 million examples, but do you have some questions first, or do you want to see about doing examples and then ask questions? Examples. Okay. Okay. Oh, shoot. Yep, go ahead.
So it's like is like one of them like the base and then the other's going to be the exponent? Like inner versus outer? That's you know what I'm saying?
I don't, so say it again, because I'm not understanding.
Okay, so like you know how the inner is like x squared plus 3
Yep.
raised? So like the inner is it's like the base.
Okay.
And then like for the other one it's like e to the 3x and that's like the exponent kind of. And that's like the outer.
Yeah, all right, so look, in this case, 3x is the inner function, and it happens to be the exponent. In this case, x squared plus 3 is the inner function. It happens to be the base. So there's no real rule that correlates the inner function always has to be... Nope, that's not what you're asking.
Well, like I was saying, like, well, I'm thinking, like,
How about we do like a couple examples and then ask again? Because I think it's not you, it's me. Like I don't think I'm getting the question. And maybe doing some examples will help you ask it differently for my sake, not for your sake. All right. All right. Someone want to take a shot at the first one? Courage for the deed. Gabby?
Okay, so will g of x equal x squared plus 3? I just did that.
All right, so Gabby's thinking. G of x equals x squared plus 3. Whoops, sorry, you said it and I wrote it wrong. F of x is...
You did it.
Okay.
And then you can do f of... Wait, I had it and I can't remember what I just said. Never mind.
You sure?
Yeah.
All right, so Gabby's getting us off to like a start thinking about which is the inner and outer function. And I would say this. Gabby said x squared plus 3 is the inner function. I wouldn't write it this way, but you can imagine it this way, right? Where x squared plus 3 is in parentheses. And that might help. Asa?
Okay, so first you would do e to the, or no, you'd be 2e.
Nah.
Yeah, it would be 2e.
Nah.
It would be because it's, oh, it's e to the x, sorry. It's e to the x, or it would be e to the, yeah.
Yep. Adrian definitely has it. So, if you were a Johnny Shortcut and I said, what's the derivative of e raised to something? You would tell me e to the something. So it's e to the x squared plus 3. 2x represents the chain, what we need to chain on to make the answer right. It's the derivative of the inner function. So
you don't really need to think about the chain rule at all. You just add on and multiply by 2x.
And don't say add on. I know it's what you mean, but you actually mean multiply on.
You need to multiply.
Okay. Great. If you feel like you don't have to think about it, that's awesome.
I didn't even start thinking about it as a chain rule until Gabby started like breaking down the g of f of x and stuff. Like,
This 2x is definitely from the chain rule, but if you don't like to think about it that way, that's fine.
yeah.
That's awesome. Way to be.
Makes things more complicated.
Do you want to ask a question about the first one before we do the second one? Because we did not seem entirely confident on the first one. You can't say that. That's like me saying, it's obvious.
Does that help on the equation where it's like f derivative g of x? I don't get that part.
All right. So f of x, right, is e to the something.
Yeah.
So what's the derivative of e to the something? All right. That's this piece. Right here. That's what this piece is. That is the derivative. Now, it's not just the derivative of f of x, because the derivative of e to the x is e to the x. It's the derivative of f of g of x. The derivative of f with respect to g of x. So the something is this piece. So the derivative of e to the something is e to the whatever g of x is, the something. All right. Then chain on the derivative of x, and that's this piece. And Zach, I'm going to be totally and utterly honest with you. I really do think sometimes the notation of the chain rule is more cumbersome than the chain rule actually is. So I know, like, Gabby started off this way, and you may very well love it, like, thinking about it this way. It's not the way everyone thinks about it. Like, I'm not positive, but at this point I would say, like, Gabby's thinking about it in terms of the rules, and Adrian, I think you're just thinking about it in terms of, like, oh, the examples we've done, this is the pattern I saw, right? So you have to find out where you fall. Like, if you feel like just the pattern's enough for you to get the rule, awesome. If you feel like you like putting it into the rule, like officially assigning it, that's great too. All right. But you know yourself as a learner, I guess, better than I do sometimes, right? So, like, you have to figure out what's going to work. Let's try a few more. All right. Zach, you want to try it? All right. All right, stop there. That's what Johnny Shortcut would say it was, right? Johnny Shortcut would be like, oh, 3 to something is just ln 3 times 3 to something. But Zach, you're no Johnny Shortcut. Perfect. I'm just going to draw that under to show you that that's the chain. That rule comes from the fact that it's a composite function.
So is it fair to say that Johnny Shortcut one day in his life will get the chain rule? Or do you think he'll be forever unintelligent?
No, that's mistaken.
No, I'm just saying
He's mistaken.
pertaining to the chain.
He's just mistaken. And Johnny Shortcut, this is his downfall. He's just mistaken about it.
Okay.
It's all right. I mean, he leads a happy life.
This is like his flaw.
Yes. All right.
Poor Johnny. I pity the fool.
Liz, you want to try? You sure? Will, you want to try? Betsy?
17 times e to the x plus 4x is 16 times e to the x plus 4.
Great. So Johnny Shortcut would have been like, oh, it's just 17 e to the x plus 4x raised to the 16th. But Betsy's no Johnny Shortcut. She says, I have to chain on the derivative of what's inside the parentheses, the inner function. So
whichever one in parentheses always can be the inner function.
If there are parentheses.
yeah, so like, all right.
That's like what I was wondering. Like, I don't know which one's always going to be in there now.
So here's the thing. 7 out of 10 times, I think if there are parentheses, that's going to be the inner function. I feel like I can probably, if I put some thought into it, come up with an example of where it wouldn't necessarily be true. But I don't. But no, see, that's the whole thing. I don't want to give you a whole hard, fast rule that the parentheses are always the inner function, because then you're going to get to calculus next year and you're going to raise your hand and be like, well, in math class last year, we said that, in parentheses was always the inner function, and then your professor's going to get mad at you and say, like, who was your math teacher? And you're going to say, oh, Mr. Barbarian from the Shipley School. And then that professor, he or she's going to, like, write me a nasty note about how I don't know about how to, like, teach math or something. So, like, I'm not coming up with a hard, fast rule. Tolly? Yeah. You're going to miss the hard one, though, Tolly. Inner function.
It could be x to the x, you know what I mean? It could be x to the 3x plus 2, and that could still be x to the x. Actually, that would make sense. Ignore me. That one.
All right. I'm all right. We're going to do something harder.
Is that 3?
Yep. I was thinking it was going to be 2, but it's not.
2.5 maybe.
Is this like 2 separate ones?
What do you mean?
Like, when I'm figuring it out, could I do it separately? And do the do the product rule also.
Yeah, you do.
So,
So Betsy's saying, oh, can't I just take the derivative of the first and take the derivative of the second and multiply them together? My answer is absolutely not.
but like, should I take the derivative first and derivative second and then use the product rule?
No. As a matter of fact, the chain rule is always going to be a question you ask yourself as you're doing another rule. It's never going to be like, oh, this is a chain rule problem. Like for C of X, that was a power rule problem. We did the power rule and asked ourselves, do I need the chain? The answer was yes. The one before that, B of X, that was an exponential rule, and we needed to use the chain. The one before it was also an exponential rule, and we needed the chain. So that you're never going to say, oh, this is just the chain rule. It is something else that needs the chain rule. So Betsy said it's the product rule, and she's right. Liz, you want to try now?
Well, I guess for the first part, it's e to the 3x.
All right, so you're going to do the derivative of the first.
And then the next one would be 5, the quantity x.
No, you're not doing the product rule.
I thought you do.
F of X times the
You were doing the derivative of the first and the derivative of the second, but that's not the product rule. Right, the Gabby?
So could you do like, wait, can you start?
All right.
So like when you do like quantity x squared plus 3 to the fifth
All right.
times.
All right, you guys just don't like doing it my way. That's fine.
Don't you first do that, like f of x and then g? Why is everyone,
Yes.
why is everyone doing it backwards?
Yeah, everyone. I don't know. You tell them, Liz. Tell them it's annoying you.
Times 5.
All right, so
Everyone does everything
the
backwards.
the first times the derivative of the second. All right. Wait, who are we? Are we back to you, Liz, or Gabby, or Betsy? Wait, who? Adrian?
Now do the chain rule.
times e to the 3x.
No, because you're.
I'll do it. 5.
All right,
5
Betsy.
times x squared plus 3 to the 5th. 4.
To the
I mean,
fourth.
sorry. To the 4th. Oh,
Sorry, I didn't mean to come off.
times 2x.
That was rude.
All right, hold on. We're not done, but we did the first part. So this is the first, and this is the derivative of the second. Where'd the 2x come from? It's the chain rule. Plus
X squared plus 3 to the 5th.
the second,
3e to the x. 3e to the 3x.
times the derivative of the first. Where'd the 3 come from?
I forget.
Where'd that 3 come from?
It's that.
ln e.
Yeah, wait, no, it's g to the 3x times 3.
It's the chain. It's the chain of 3x, right? The derivative of e to the 3x is e to the 3x and chain on the 3.
Yeah.
It's the chain.
Correct.
Okay?
Yes.
We should do some more.
Yeah. I mean, that's not, the problem's not done?
No. Sorry.
The problem's like,
The problem's finished. We should do more problems, is what I'm trying to say.
Didn't really understand.
Do you want to ask a question? I feel like we've been doing it enough now that you should have an idea of the questions you need to ask.
How many rules are there in total?
I think there are like maybe 8 or 9 different rules.
22. I would die.
And the thing that's going to be increasingly frustrating is that there are going to be more and more rules and you're not going to know exactly which to use.
Yeah.
And that's going to be the hard part. Not knowing the rules. So here's the thing. I have to be upfront and honest. Memorizing the rules is the easy piece. You have to do that. Whatever it is, flashcards, that's a given. The hard part of this is knowing when to use which rules. That's the challenge. That's what makes taking the derivatives hard. Not memorizing the rules. I can have a 7th grader memorize the rules, right? But you all have the conceptual understanding of figuring out when to use it. That's the hard part. Asa?
Okay, so, quick question. So in this situation, are we not even using the chain rule? Because it looks like we're just using the power or the
No,
product
we
rule.
use the chain rule.
But where? I don't
Yeah,
see it.
Because when we did derivative of x squared plus 3 to the
Right.
fifth, you have to use the chain rule.
Right.
The
So
parentheses is the inner and the 5 is the outer.
Oh, okay, I see. So what is the original f of x function? Just e to the 3x?
well, all right.
F of x equals
This gets incredibly
X to the
complicated because they're both composite functions,
Yeah.
right?
Yeah.
So if you say that this is f of x, that's actually a composite function. That's really f of g of x, where f of x is e to the x and
So
g of x
it's
is
just
3x.
multiple composite functions. and
Yes.
You're just separating it via the power rule.
Yes.
Or the product rule.
Yes.
Okay. that
So-
makes sense.
And this is what I'm saying. I think sometimes when we try to make it fit the rules, like assigning f of x and g of x, for some people that works really well. For other people, it doesn't. I'm going to be honest with you. I'm on the side where I think through the rules and don't necessarily assign f of x and g of x's, and that works for me. And I realize that that might not be what works for you, but when you see me do them, I'm probably going to say like, oh, it's a product rule, and we need to remember the chain rule, things like that.
Do we get partial credit on this?
On the quizzes, yes. On the tests, no. 1 million.
10. But not actually 10. But like some value of 10.
Alright, let's piece this one out.
All right. Who wants to try it?
I will.
All right.
It's
Considering
the
some
quotient.
more.
It's the quotient rule.
The x's. It's not like the same thing as saying after.
Blow
That's
in your
confusing that you're saying
face.
it like
Like what?
The-
Oh, fun.
you know what
Okay.
I mean?
Take on that, John.
Hold on.
Why are we changing it?
It bothers Betsy.
Oh, Bob
Okay.
is back.
It was weird.
So you said it's before we do it. You said it's what?
Quotient.
Quotient rule and chain and product.
Oh my god. Oh, great.
So you can see how like this went from easy to hard. Yep. Yep.
Let's get this
Do
nastiness
product
over with.
first.
Yeah, let's do product.
Yes, do product.
Well,
Do this training, guys.
I don't think you can just do the product first, because if you're just doing the product, all you're doing is taking the derivative of the numerator. But the quotient rule says you don't take the derivative of the numerator. If you have a quotient, you need to do
Low D high.
low. All right, so let's start with low.
High.
3x squared plus 7.
This is nice. I like
D high. First. What'd you say, Gabby? Oh, I should
it.
change.
Times 2x.
No, this is the product.
Yeah.
Isn't it?
So there's the first times the derivative of the second,
Oh,
Yeah.
plus
plus
x squared
the second
times e to the x.
times the derivative of the first.
Dang, anything else?
Okay, so there's low D high minus high e to the x times x squared. D low all over. I actually don't think we used the chain rule on that. Is that true?
Well, you use it with the e's. Don't you?
But we didn't in this case.
No, it isn't.
That was freezing.
Well, this is the derivative. I'm not taking the derivative of the bottom. If I was taking a second derivative, yeah, maybe. Sorry, I didn't even use the chain in that, but do you see how ugly that is? Yeah, right? All right.
I think that that's good.
I do think that's good.
Not very
So,
simplified, but
here's the thing. We have like 3 minutes, right?
No. Yeah.
When do we-
108. Oh, do the little thing up there.
Wait, we're done?
108.
Yeah, okay, fine. All right. So you're going to need to practice tonight, right?